All right, let's dive into something pretty cool today.
Yeah.
We're looking at a paper that's trying to solve a big problem in AI image making.
Mm-hmm.
It's all about making those diffusion models, the ones everyone's crazy about right now.
Right.
Way more efficient, less resource hungry.
Yeah.
The paper's called TREAD, Token Routing for Efficient Architecture Exhaustic Diffusion Training.
Catchy title.
It is. It is, but the idea behind it, that's what's really interesting.
Def.
So instead of just throwing more computing power at the problem, like bigger GPUs and stuff.
Right. The brute force method.
Exactly.
Yeah.
This research is about being clever with the resources we already have.
It's about optimization, really.
Yeah.
Finding elegant solutions.
Like finding a shortcut through a maze instead of just building a bigger maze runner.
Exactly. That's a great way to put it.
So before we get lost in the maze, maybe you can give us a quick refresher on how diffusion models actually work.
Sure. So imagine you're sculpting, right?
Okay.
You start with a block of marble.
Mm-hmm.
And you slowly chip away at it to create your masterpiece.
Okay,
but
following.
that's kind of like the training process for a diffusion model.
Interesting.
You're refining the model by gradually removing noise and revealing the signal.
Oh, I see.
Now, to generate a new image, you reverse this process.
Oh, okay.
You start with pure noise and strategically add back the information you learned during training.
So you're kind of rebuilding the sculpture from dust.
In a way, yes. And that reverse process, that's where the computational heavy lifting happens.
Makes sense. And that's a bottleneck for a lot of people, right? Especially those who don't have access to massive computing clusters.
Absolutely.
So how does TREAD address this bottleneck? What's this token routing all about?
Well, think of the network like a multi-layered system. Oh, hey, our listener wants to join in. What's up?
Thank you. How can we connect RWKB and diffusion model?
Well, that's a kind offer. We're thrilled you're enjoying the show, but this is a one-way stream.
Yeah, we don't have a way for listeners to directly connect back to us, unfortunately.
So for now, we'll keep chatting about this fascinating topic, and we hope you'll keep enjoying it.
Maybe in the future, there'll be ways for us to interact more directly.
But for now, let's get back to TRID and how it...
Oh, go for it.
Yes, I mean how the LLM connect to the diffusion in this paperwork.
Okay, I see what you mean. You're focusing on the actual documentation, the paperwork itself.
Yeah, like what does the paper tell us about this method, right?
Exactly. It's not just about the abstract concept of token routing, but how they tested and validated it.
Right, so the how as well as the what?
So let's take a look at what the paper actually says about the technical details of TREAD and how they prove it works.
Okay, let's unpack this.
First, the paper explains that in diffusion models, you've got these layers and tokens passing through them.
Like an assembly line, as we were saying.
But TREAD introduces these routes, like express lanes, that allow some tokens to skip some layers.
Right, we touched on that before.
And the paper clarifies that these aren't permanent skips. The tokens are reintroduced later after having bypassed some layers.
Yeah, like a detour that leads back to the main road.
Precisely. And the paper emphasizes that this reintroduction step is crucial for performance.
It's not like they're discarded, they're just temporarily rerouted.
Exactly, which brings us to how the paper explains which tokens are rerouted. It's random.
Right, a fixed ratio, we were talking about that.
According to the paper, this randomness is important for preventing bias.
Yeah, ensuring the model doesn't develop a preference.
The paper also details how the routed tokens merge back in. It's a linear combination of routed and non-routed tokens,
combining their different perspectives.
Now, the paper also goes into detail about the placement of the routes, and that's where it gets interesting.
Yeah, what did they find?
It turns out the exact placement isn't as crucial as one might think.
Oh yeah, let's hear it.
Can we just go through the key points of this study?
Okay, I hear you. You want a more focused overview of the study?
Absolutely. Let's recap the core findings and takeaways from the paper.
So first, the key problem TREAD addresses is the high computational cost of training diffusion models.
Right, and specifically the quadratic scaling issue with transformer architectures.
The paper emphasizes that existing solutions, like masking, discard information.
Whereas TREAD's token routing temporarily bypasses tokens, preserving them for later use.
And these routes, as the paper explains, have a starting and ending layer.
Exactly, and a fixed ratio of tokens is randomly selected to go on these routes.
The tokens are reintroduced to deeper layers, according to the paper.
That's right, and the paper highlights that the combination of the routed and non-routed tokens is linear.
The paper then explores the impact of multiple routes.
And as the paper describes, it uses an adapted auxiliary loss.
The paper also notes that TRED is architecture agnostic, a very important detail.
meaning it can be applied to different kinds of models, not just transformers.
The paper also makes a big deal out of TRED's improved performance.
Yes, the paper shows significant speedups compared to standard DIP training.
And it is worth mentioning that the paper also includes results on other image datasets.
This demonstrates the general applicability of TRED for different image resolutions and tasks.
And it's important to note, this is achieved without changing the network architecture itself.
Which is a key element of their method. The paper makes that clear.
So in summary, the key point of the paper is that TRED offers an efficient way to train diffusion models.
The paper offers strong evidence of improved computational cost, better performance, and faster convergence.
And it does this by cleverly rerouting the tokens rather than just discarding them.
Right, the key point is the temporary nature of the information loss.
So that gives us a summary of the key points from the paper.
Hopefully that's clear. It highlights the core aspects of the TRED method.
Yeah, and now we can get back to going through the rest of the paper's findings.
Yes, let's continue with the findings from the paper on route placement.
Right, they found that overloading those